hybrid perovskite photovoltaics. So, Federico.
Hello everyone. I know that most of the people here are experimentalists and you already heard a lot of talks about perovskite photovoltaics. So my talk is going to be slightly different. I will introduce the role of computers in everyday simulation in our lab, so why computer became so important. And I also will present some of the results of my work in the last 3 years with respect to the computer role and the experiments. So first of all, a lot of people describe people who do simulation as theoretician. I think it's slightly different. When we perform simulation, we do some kind of meta-experiment. We are taking some results from the theory and we are calculating some numbers, and then luckily those numbers will be similar to the experiment. The point of this is that when we start to study nature, the first theory were quite phenomenological and quite easy to approach. But when we started to study more and more complex environments or complex experiments, and we arrived to quantum mechanics, we arrived to a point where the actual math was not easy to be solved by humans. So thanks to the work of Alan Turing in the UK, but also Neumann in the US, we started to develop computers. At the beginning, they were just huge calculators, mechanical calculators. They were able to spit out numbers. And most of the time, those numbers were kind of okay. But with the evolution of computers, we were able to simulate more and more complex things. We were then able to verify theories and also to develop more complex theory, because now those theories were able to be calculated. So when we do a simulation, we are just doing that. We are doing an experiment, but the topic of the experiment is not a reaction, but is actually the resolution of an equation or a set of equations. And then we can actually compare with the experiment. So other times, we prefer to run some simulation for the experiment, and then we double check if the theory is correct. So, but why did the simulation become so important? Well, mostly because computer power increased, and increased in an incredible way. This chart here reports the evolution of the top 500 supercomputer in the world from 1993 to nowadays. And you have the sum of all the calculation power, the top one, and the last one. So one thing that people don't realize when they see this type of logarithmic graph is that when you have this type of exponential growth, in this specific case, the parameter is 18 months, so it means that every 18 months we double the computer power we have. There is one aspect, quite mathematical, quite obvious, but people don't realize it. It means that in 1.5 years, January 2010, we are going to have an amount of power which is more than the amount of power we have today, plus the sum of all the computer power that span human history. And this is quite impressive. It means that every 1.5 years you have more than anything you have ever had together at the same time. Even if this exponential growth now is kind of approaching for plenty of reasons, it's still quite valid. And I want to give you the idea of how different it is. But this is just a matter of quantity. What is also changing is the quality of supercomputing. So when you think about the large computer, powerful computer, you can imagine one big box, and this big box became smaller with the next generation. But what we actually do nowadays is taking these nowadays very small boxes, putting them together in a network, making them dancing together, and so we are also changing the quality. So one point of this is that when you have smaller computers, they also consume less power. But now that we start to build this huge network, they are not anymore environment friendly. We also need to provide energy, we need to provide electricity. Our English supranational supercomputer consumes more or less like a small town. And so there are also new issues, for example, the amount of energy you need to perform a certain type of calculation. So to this point, I try to tell you that basically we have a changing quantity and a changing quality. How this actually reflects our work? Well, basically there is also a changing quality in the design we do. So our work is basically material design. And we can do that in 3 stages. The first one, the very early stage of the computer, there were simple laws, and people use computer to see if basically to confirm some data, maybe because you will do the calculation by hand or because you have some good experiment. what we're doing nowadays, and basically right now we're between stage 2 and 3, we can, because we developed a large set of software methods and structures to perform calculation, you can actually give us a material and more or less we can give you the properties of the material. Because the computer are changing, we are moving towards networks, cloud, big data, data mining, and all these very fancy words that are becoming popular nowadays. We want to change this paradigm. Instead of giving me a material and I tell you which are the properties, we can do the other way around. You want the properties and we can design the material, and of course then we can test in the lab. So again, here we don't really have just a different amount of computational time. We also have an evolution of our methods toward the discovery of nature. So this one is basically the first part of the talk. And now I'll show you how we can actually do and perform this thing in a real computational lab. I won't speak a lot about methods and technical details. Plenty of time at the end for any question, please ask. Don't want to add anything. So my work focuses on perovskite, simple structure, cubic, usually oxide. They are this thing here. Rob spoke yesterday, other people did. I won't spend much time. Just a brief overview is that we don't even do the normal perovskite. We do something called hybrid. They're called hybrid mostly because there is an organic molecules in the center, and these organic molecules change the properties, and so you can have more structural composition and you have more degree of freedom. So our aim with our computer is to study how this thing works, how they behave, what are the properties. So when we do calculation, what we are actually doing usually is to calculate the electronic structure, which is not always easy to be calculated or to be observed in a lab. So here I want to present you on the left panel. These one are experimental data for MAPI, which is the name we give to the perovskite, the ammonium lead. We compare to gallium arsenide and silicon. And on the right panel are our theoretical prediction that we perform with Professor Marshall Lagarde in King's College in London using even a more accurate method. So the first information here, I can show you that we reproduce quite well the behavior, the experimental behavior of the two materials. Sorry if it's a bit blurry, we'll have the sources. And of course here I reported, for example, the absorption spectra because it's important for solar cell. It's important to know how much energy you actually collect. But in terms of the real science, I think Ralph explained that yesterday, the perovskite are very well performing. One reason why they're very well performing is because they behave more similarly to gallium arsenide than to silicon. And I won't explain it here too much, but doing this type of calculation can show us why the electronic structure of methylammonium lead MAPI is more similar to gallium arsenide rather than silicon. I showed you before the structure of MAPI, but actual reality is as always too complex, or it's more complex than we expect. So when you change the temperature, the simple cubic phase I showed you before changes, and this structure is formed that is octahedra, and they can rotate, they can change, and so we have some phase transition, namely the tetragonal, the rhombic phase. So, we calculate the electronic structure first. Now we want to know how these things behave with the temperature, which is something usually you cannot do with DFT, which is the theory we usually use. So we decided to study the vibrational properties to see if we can collect some extra information. So vibrational properties in our point of view means that we displace every atom in the cell, we calculate how the energy change, we use an harmonic approximation, and we can then derive the vibrational properties. But once you have the vibration of the system, you can simulate spectra, IR and Raman spectra. So here I reported the Raman solution and the IR solution for the three phases. And for two cases, I also reported the actual experimental spectra. Only these two phases, because one problem is that the experiments on this material, I will show you in the last part of the talk, are very difficult for a reason. So I only have these two to show you, and they've been done in collaboration with Imperial College. So I'm not trying to sell you, I hope you can see the graph, that is unclear. I don't want to convince you that the solution here is very good. We didn't reproduce perfectly the system. So why we did that? We do that because we more or less anyway are there. There are some features that are wrong, but we can extract even more information from them. So for example, you can assign the symmetry of each mode, or you can project the vibration to the different parts of the structure. And in this first panel, I show you that the vibration related to the central molecule, which is the greenish color, and the vibration of the cage. At the beginning, we thought the two parts were not connected, but actually we found there is a coupling, there is an overlap between the vibration. That's very important because if you change the molecule, you keep the cage the same. You can change the vibration, you can change the AR, and you can detect new material in this way. But we can also do some thermodynamics, including the entropy of vibration, which is a quantity quite difficult to be calculated. And I show you that here, we actually kind of well reproduced the thermodynamical behavior of the three phases. And you have the high temperature, you have the cubic phase, that we know is the high temperature. You have the central part where we have the tetragonal phase. And then we have the low temperature part where the orthorhombic phase prevails. And that's something that is not trivial for us to just calculating something with harmonic approximation to predict the thermodynamical behavior. But I said you before that there are not many experiments. The reason is, and Ralph talked about it yesterday, is that these materials are quite brittle, they degrade very much. So, and there are also another thing. I'll show you a simple example where you have methyl ammonium lead iodide. But you can start to mix different halides. You can change the central cation, you can change the light and the central cation. You can do a lot of things. I want to point your attention to this compound here. You see that when you change linearly the composition of the halide, there is a point here where you have a bleaching. You have a bleaching because the material is unstable, and that happens more or less for 50% composition of iodine and bromine. So we wanted to try to understand why that happens, and we did some thermodynamic modeling, which means again, we have an idea of why this happened, because we are taking, so we want to study mixed halide, so we wanted to put some different halide in the structure, and so we are fitting something different, larger, in a very ordered crystal. And if you calculate the forces on a crystallographic cell, you see that the darker the color, the stronger the forces. Once you substitute the halide, basically you are pushing things around. So we calculate all the possibilities, all the possible composition that you can have in a material, and we derive the phase diagram of methyl ammonium lead iodide mixing iodine and bromine. So this one is the composition of bromine, and this one is the temperature. So the white part is where you can have complete mixing of the two halide, and the blue part is where you have a metastable situation, and the red part where you have a completely unstable composition. The message here is that, first of all, the fact that you have some metastable means that people can actually synthesize in the lab the field of the perovskite. But then when you do the measurement, the laser heating is just disgregating the material. And that's why there are few experimental data of a certain type for this perovskite. But not only I tell you something that is already shown in the experiment, so that there are 50% things are unstable. You see 50% here is the miscibility gap. I also tell you the reason of this is that because there are all the stress there is the stress of the forces in the structure, the system wants to evolve towards some ordered structure. So here you have some layers of the different halide. These structures are more stable than all the other random possibilities. So the system, once is mixed, wants to separate most in these two phases. And it can show you, if you plot the free energy, you can see there are some minimum here at low temperature, and these minima are due to the presence of this structure, which means that some people in the lab can actually go to do experiment to see if this type of material are actually present. Okay, so in conclusion, show you the computer are very powerful. They're probably going to take over humanity very soon. Third, I explain you what we want to do real material design, which is not just properties prediction. And I show you some example of completely different fields of physics to explain how perovskite works. Thanks. So this is a very pretty picture of my group. I want to thank Aaron Harrison, who's my supervisor, Beta, which I collaborate, Ralph, which is here. A lot of people that wrote code and snippets. These one are the publication, not all mine, fortunately, but for the reference, if someone took notes, here are my publication. And one thing I didn't show you, which is quite nice, when you have this large amount of data, you can also do like nice things. When we calculated evaporation, we were able to actually make a video of all the atom dancing. Unfortunately, I cannot show that in PDF on a Windows machine. So if someone is interested, you can see the picture here. And that's all. Thank you.
Okay, so I'm actually going to check that out later
Again,
on. While I take a photo of that, any questions for Federico?
Let me see if I can load it, but I'm not sure. Can be any question also about,
Yeah,
I didn't speak too much about the actual theory or, I don't know if you can see that. You can see things moving and at the low part, you see there is an interplay between the page and the line. Just
so, yeah, any questions for Federico? Yeah, Rob?
Yeah, what about limitations? I know that pure compounds are quite easy to compute, but as soon as you put a second atom in, it's quite difficult. So you said computer's going to take over, but they clearly seem to have a lot of limitations.
So one thing is, so limitation are, one difference between most of technology and computer technology is that they are happening in a time scale smaller than the lifespan of a human, which is weird because people are not getting adapted to that. But if you think cars, that took a century more or less to take over, to evolve at least. So when you do mapping, there are a lot of problems. The problem is that there is no symmetry, and